All right, the fourth reaction type that we're going to go over is single replacement reactions. And this is a reaction that you'll be able to recognize based on the reactants. You'll see an element reacting with a compound, and that's how you'll know that it is a single replacement reaction. When this reaction proceeds, you're going to make a new compound and a new element. And that element will come from the original compound. So you can see here that A, whatever A is going to replace B in this instance. Now, replace does not mean bind with. Replace means kick it out of its position and take that position. So notice that A is now bonded with C, and then B is now the element that's all by itself. Okay, so that's just a model of how this reaction proceeds. Some important things to know about single replacement reactions. They occur in solution, which means typically you're going to have a big old beaker of water and your chemicals are going to be dissolved. The reason we do single replacement and double replacement reactions in solution is because solution chemistry is faster. When ions are dissolved, they can move quicker. The chemistry itself will happen faster. So you're going to see a lot of aqueous phases, whereas before with combustion, synthesis, and decomposition, we did not see that. And a different note, and this has not been the case for us thus far, not all single replacement reactions happen. Just because you set up a reaction, just because you put two chemicals in the vicinity of each other, does not mean that anything's going to happen. It's going to depend on the relative reactivity of the reactants. Okay, and I'll definitely talk more about that. And then there are also two different kinds of single replacement reactions. We have metal replacement reactions, and then on the back side of this, I'll discuss non-metal replacement reactions. So going back to this phrase right here, relative reactivity, that is what determines if a reaction happens or not. In a metal replacement reaction, if you have an element that is more reactive than the element that's in a compound, that reaction will proceed. Okay, now that was just an atrocious way of explaining that, so let me segue over here. This is the activity series of metals. This is not a comprehensive list by any means. There are a ton more metals on the periodic table than just these, however many there are. But this is a good representation, and it gets the point across. It is a list descending in the amount of reactivity of these particular metals. So you'll notice up at the top we have things like alkaline metals and alkaline earth metals, things that we know are very reactive. All right. Down here at the bottom we have things like copper and mercury, silver, gold would also be down here. These are elements that are very, very stable. Traditionally, or, well, no, that works. You're going to have more of your transition metals down here at the bottom, alkaline earth metals up here. One interesting thing to note is that hydrogen is in this list. Now, hydrogen is not a metal, but it does form a cation very often, just like all of these atoms, and thus it can take place in these metal replacement reactions. It can get kicked out of a compound or do the kicking out. So if we are comparing two elements on the list, the one that is higher up on the list is going to be the more reactive. So lithium is more reactive than potassium, is more reactive than calcium, etc. The reason that this is pertinent is because if you have an element, you know what? No, I'm just going to give you an example. So here's an example. Let's say that we have potassium and magnesium hydroxide. Okay. Last week we talked about phases. All right. Potassium is just going to be a solid. Magnesium hydroxide. Remember, this is all happening in solution. For now, we are assuming that all ionic compounds are aqueous. That's not true, of course, but that's what we're going to work with for now. Okay. We have this potassium element, and it is going to try and get into the compound. All right, it's going to do that by replacing the metal in the compound. And the reason for that is because potassium itself is a metal. It doesn't want to bond with the magnesium. All right, that would be two positively charged ions trying to bond. That doesn't make sense. It wants to bond with the hydroxide. Now, what's going to determine whether or not this reaction can proceed is the relative reactivity of the potassium and the magnesium ions. So if I go over here and look on my list, here's lithium, here's magnesium. Lithium is far more reactive than magnesium. Okay? Now, if an element is reactive, that means it wants to give up or take electrons. It wants to go through some sort of chemical process to become stable. All right, now all of these things want to do that. But the more reactive the element is, the more able it is to do that under a given circumstance. So, here we have potassium. It is more reactive than magnesium. What that means is this reaction will proceed. Potassium can kick out magnesium. So magnesium has to go be by itself. It's very lonely, it's very sad. And the potassium will bond with the hydroxide. Okay, so K is 1 plus, OH is 1 minus. We're going to make K OH. Okay, so magnesium will actually precipitate out solid magnesium with this reaction. And then again, we're just going to assume that all ionic compounds in the solution are aqueous. Only thing left to do would be to balance this reaction. So I would need to produce 2 potassium hydroxides, and that would use up 2 potassiums. Okay, so this reaction does happen because potassium is more reactive and magnesium is less reactive. And I knew that by comparing their relative position on the activity series. Okay, here's an example where the reaction will not proceed. Let's say that I have solid copper, okay, just some copper metal, and let's say I try and react it with magnesium hydroxide. So same reactant as this first example where we did have a reaction proceed. Again, we have a metal trying to replace another metal. Okay, so copper is going to try and replace magnesium in the compound. Let's see if it's able. So here's magnesium on my activity series, here's copper. Magnesium is more reactive than copper. Notice that magnesium is already in the compound. Okay, that means that this reaction is not going to happen. And what we do is we write NR for no reaction. Okay, copper basically doesn't have the gumption to kick magnesium out of this compound. The way I like to think of it, your more reactive element, in this case magnesium, is more clingy. It needs to be in this compound. It's more codependent, if you will, if we're going to use some psychological phrases. Copper, more stable, okay, more independent, more able to just kind of hang out by itself. So that's why this reaction doesn't do anything. All right, if it was switched, if the magnesium was here at the beginning and the copper was in the compound, then magnesium would kick out the copper. All right, so that's an example in which nothing happens. Here's another example for you. So let's say that we have aluminum, and we're going to react it with silver chloride. I apologize if you can hear Skylar in the background. She's having a little weird baby nightmare. It's very sad. Okay, without thinking about this too much, I should know that this reaction is going to proceed. Silver is one of the most stable elements on the entire periodic table, second only probably to gold. So this reaction is going to happen. Just about anything will kick silver out of a compound, anything but gold. So aluminum is more reactive than silver. This reaction will happen. The aluminum is going to bond with the chlorine. We'll make AlCl3. We're going to kick out the silver. Silver has to go hang out by itself. And that's your reaction right there. Okay, your aluminum chloride will be aqueous. Your silver will, of course, be solid. Okay, to balance this, we're going to need 3 silver chlorides, which means we'll produce 3 silvers. Okay, now because aluminum and silver are separated by quite a few elements on this activity series, okay, this means that this reaction will happen pretty darn fast. Okay? The larger the difference in reactivity between the 2 elements at stake, the faster the reaction will happen. Okay? Here's another one. If we have zinc, right? Let's say we have a piece of zinc and it's put into this iron 3 bromide solution. This is another metal replacement. The zinc is going to attempt to replace the iron in the compound. To determine whether or not this will happen, we consult our activity series. We notice that iron and zinc are right next to each other. Zinc is more reactive than iron, so this will proceed. We'll make zinc bromide. Remember, zinc is always a 2+. And then we'll kick out the iron, and that will be your new element. So there's an aqueous compound and then solid iron. This reaction, because zinc and iron are right next to each other in this activity series, we can surmise that this reaction would happen rather slowly. It'll happen, but it's going to take a while. Okay, because zinc, while being more reactive than the iron, isn't much more reactive, just a little bit. So it'll happen, but quite slowly. Okay, a couple more examples, just because I want to talk about the hydrogen that can be involved in these reactions. So here's one where we have a metal that's placed into a solution of acid. And let's just make it nitric acid. So HNO3. Okay, acids are always aqueous. Calcium all by itself is just going to be solid. Okay, calcium is a metal. It's going to do a cation replacement is another way we can describe this, because hydrogen is not a metal, but it is in the cation spot. So what I have to do is compare calcium and hydrogen. Yes, calcium is more reactive than hydrogen, so this will happen. Okay. So the calcium will kick out the hydrogen. It's going to react with the nitrate, so we're going to make calcium nitrate, CaNO3 Hydrogen gets kicked out, has to be by itself, but remember, hydrogen is diatomic, so it'll form a gas. Okay, and then of course, balance. Okay, so that's an example where we have a metal reacting with an acid. What about if we have a metal that's trying to react with water? Some of these reactions happen, some of them do not. And that's because water is very, very stable. So for instance, let's say that magnesium is trying to react with water. Now magnesium is an alkaline earth metal. It's pretty reactive, but not nearly as reactive as the alkali metals. If we consult our chart here, yes, magnesium is more reactive than hydrogen, but we have this little note here. Okay, these four right here, lithium, potassium, calcium, and sodium, those are the ones that can react with water. All right, these other elements that are above hydrogen will be able to react and kick out hydrogen from an acid, but not from water. So this would be an example where we have no reaction. So let's try again. Let's try and react water with a more reactive metal. So let's just do potassium. And I'm going to rewrite water as HOH. Okay, it's still H2O, but then I can see my cation and my anion. My cation would be the hydrogen, my anion would be the hydroxide. Okay, so I try again. Here's hydrogen, here's potassium, much more reactive than the hydrogen, and it's one of our four that can kick hydrogen out of water, so this will happen. It's going to kick out the hydrogen. It's going to react and bond with the hydroxide. We'll make KOH. And then once again, H2 will come out as a gas. So this time we have a liquid. All right, our compound is going to be gaseous or aqueous, and then the hydrogen will be a gas. Okay, so those are metal replacements or cation replacements. We also need to talk about anion replacements or nonmetal replacements. This won't take nearly as long, I promise. So a nonmetal replacement, if you have a more reactive nonmetal element, it will replace a less reactive nonmetal element. So it's the same concept as metal replacements, where we have this activity series. We just have a small reactivity series of nonmetals. So fluorine, no surprise there, is going to be the most reactive nonmetal, and this is not an inclusive list, but just of these ones, phosphorus would be the least reactive. So just about, well, any of these would be able to kick out phosphorus. And that's pretty much it. Otherwise, it works exactly the same. You just have to realize whether you're doing a metal replacement or a non-metal replacement. So let's say that we've got chlorine gas, so chlorine's right here. and it gets bubbled through a solution of lithium bromide. Fluorine gas. Okay, ionic compound, we're going to assume that it's aqueous. Okay, so this time our element is going to kick out the non-metal, and it's going to bond with the metal. All right, the question is chlorine more reactive than bromine? We got questions on the activity series, and yes, chlorine is more reactive than bromine. This does happen. Okay, obviously these are both 1- ions, so this is really easy. We would make LiCl and take out the bromine, which is of course diatomic, so we'd form Br2. So another aqueous and a gas. Okay, so that's an example of a reaction that would proceed. If we had, again, chlorine, let's say that it was trying to react with magnesium fluoride. All right, chlorine's a gas, magnesium fluoride would be aqueous. Now, fluoride or fluorine is your neediest, if you will, nonmetal. It's the most reactive. If fluorine is already in a compound, nothing's going to kick it out. Okay, so this would be an example where we have no reaction. Okay, so I'll give you one more. Here's fluorine as an element. So when I see this, little alarm bell should go off. You know a reaction is going to happen. Fluorine can kick out anything. All right, and let's say that it is getting bubbled through a solution of sodium phosphate. So again, diatomics we assume are always gases. Sodium phosphate's going to be aqueous. All right, fluorine, just for kicks and giggles, here's fluorine, here's phosphorus, definitely going to happen. And not only is it going to happen, it's going to happen real darn fast. So the sodium will bond with the fluorine, we'll make NaF, and then we'll kick out phosphorus all by itself. Okay. So that will be aqueous, and then phosphorus as an element is a solid. And the last thing we would have to do is balance. Let's see, I think I'm going to need to double that. Yeah, because I have my diatomic right there. Okay, so that's single replacement reactions. We've got metal replacements and non-metal replacements. That does make it a little bit more tricky, but the other thing that you have to consider is, will the reaction happen or not? And to decide that, you must of course consult your activity series.